Yeah, so today we begin kind of the second part of the class. Specifically, up until last week, we were focused on the bottom half of our usual roadmap, specifically where we focused on methods for optimal control. So if you recall, we started our discussion through open loop methods, and namely through the lens of indirect and direct methods, where the goal was to compute an optimal trajectory from a given initial condition. We then, this is great because they are fast and reliable, but they are specific to the given initial condition where we are in. We then moved towards the closed loop section, namely through dynamic programming and Hamilton-Jacobi-Bellman or Hamilton-Jacobi-Isaacs equations, where there the focus was on computing an optimal control policy, that is a function that maps states to optimal controls. And we saw how this was definitely more powerful, at least in principle, compared to the open loop framework, because it gives us a rule of how to behave independently on the state in which we're in. But at the same time, this came with an important computational expense. And so last week, we focused on MPC, or Model Predictive Control, which is basically a framework which tries to get the best of these two approaches, namely achieve the performance of closed-loop methods through the recursive solution of open-loop optimal control problems. Underlying all of these methods was the assumptions that we knew how the dynamics behaved. So we always knew that we had a good representation of our dynamics, which came from maybe an analytical expression or a differential equation that represents our dynamics. And so in the second part of this course, we kind of relaxed these assumptions and we move into the learning-based setting where we assume we do not know in advance the dynamics of our models. Yes. And so specifically for today, we will be, first of all, transitioning into the learning-based setup, giving a rough idea of the kind of topics we'll be discussing. And then we will be approaching specifically the top left part of the quadrant, which relates with more classical ways of dealing with learning, specifically regarding system identification and adaptive control. And we'll see two examples of adaptive controls, namely MRAC, or Model Reference Adaptive Control, or MIAC, Model Identification Adaptive Control. And as a general setting, so remember the framework, the setting we are in. So specifically, we look at controlling some system through the definition of a controller or a control law. And in order to control the system, we may be measuring. We are having some sensors which measure the output of our system. And we might want to compare the measurements that come from our sensor with some reference, which you have in mind, that is an ideal behavior of our system that we would want it to execute. And this will lead the construction of our controller. And so we have this feedback loop, which happens kind of in closed loop. However, the question is, what happens in the moment where we have some uncertainty or some unmodeled effects in how the system behaves? And so this is exactly the setting in which we'll be working on today and for the rest of this class. And so fundamentally, so when looking at dealing with this kind of uncertainty that could be present in our system, how can we handle this? And so kind of a simple approach could be that in many cases, uncertainties may have only a small effect. So for example, consider we're trying to fly a drone and we might have some unmodeled wind effects which are still pretty small. And so in this case, perhaps, we don't really need to do anything too sophisticated about dealing with this uncertainty, but having a feedback controller may be just enough to compensate for this unmodeled effects. And so this could be as simple as we have some reference trajectory for our drone that we want to follow, and we might want to build a sort of feedback controller that tracks this reference trajectory, for example, through Ph.D. control. But again, we're in the system where we might have some unmodeled effects. If these are pretty small, then maybe feedback control is good enough. A second approach is we could try to be a little bit more sophisticated and going into, for example, robust control approaches. So we discussed last week or a couple of weeks back, if you remember, kind of min-max formulation where our goal was to maximize some measure of reward, which had a form of this type, maximize with respect to our controls U, and we were assuming there was some distribution gamma, set of distributions gamma, which were basically playing the role of the adversary. So essentially modeling the worst case possible disturbance that could affect my system. And in class, we were looking at this relatively sadistic example of the homicidal chauffeur. But this is, if we see this from the perspective of dealing with uncertainty, it is as if we're saying we have a system with some uncertainty, which we are not aware of, things we cannot model. And so let us be robust with respect to this uncertainty by reasoning with respect to the worst case scenario possible. And so, of course, this is on one hand great, but it could come with behavior that is potentially too defensive and a little bit too conservative. But again, this is a valid second high-level strategy of approaches. The third one, which is also the one we'll be specifically focusing on today and for the remaining weeks, is the one where we have some uncertainty and we take into consideration the fact that we can collect examples of behavior and state transitions in our environment. So again, consider the case where we have our drone flying to accomplish some task. We might be storing logs of previous flights in order to observe these state transitions and use those to learn from data an approximate model of our dynamics. And so this is exactly the setting we'll be working with. But I think this is a nice kind of frame mental model to have, in the sense that whenever we have some uncertainty, we might be good enough with some feedback that in order to correct for our model effects. We might want to be extremely conservative and reason about worst case scenario possibles, or we could use data-driven approaches that leverage pre-collected state transitions observations in order to learn an approximate model of our dynamics. Any questions on these high-level and macro categories of methods? Okay. And so in the moment we zoom in our third of these macro categories, that is data-driven methods, kind of the question that comes to mind is, okay, we say we want to learn something, but what can we learn? And at a high level, I would say that different methods for learning-based control typically divide themselves across two main families of approaches. In the first one, we want to use measurements or collected episodes or transitions in order to directly improve the controller. On the other hand, we might want to use these measurements to learn an approximate model of our dynamics and then use this model to improve the controller. So you see that in the second of these two families, we have this intermediate objective, which is kind of system identification in a way, which is then a proxy to improve our overall controller. And so the types of methods that we'll see today and for the rest of this class kind of loosely fall within these two buckets. And so today we'll be focusing at direct adaptive control and indirect adaptive control, as well as system identification. But in the coming weeks, we'll also focus on imitation learning, as well as model-free and model-based reinforcement learning. Okay, and so as a second question that comes to mind would be then kind of how does learning actually happen? And specifically, there are three, I would say, prototypical cases. The first one is the 0 episodes case, which is also known as the kind of system identification approach. And the assumption here is that we have, in some way, pre-collected a data set of state transitions or rollouts, if you wish, of some policy controlling our system. And we might want to use this offline data set to improve our controller. This could be directly improving the controller, or it could be learning a model to then improve the controller. But what I want to stress the fact here is that this 0 episodes case essentially entails having some mechanism of collecting a data set, completely offline. And then we use this data set to estimate some parameters or some models in order to improve controller performance. This is to be distinguished from the one episode case, where we want to have this adaptation and learning happening directly online as kind of while we control the system. And I think, kind of again, taking our kind of drone example, say that we have some quadrotor that is carrying some payload of an unknown mass m. The one episode or online adaptation approach would essentially mean that we have no mechanism of kind of estimating this mass m from previous flights, but this is something that we have to estimate and adapt to online while we control the drone. And so the goal here would be to, while we are controlling the drone, estimate some unknown parameters, such as, for example, the unknown mass of our payload. And then a third category of approaches is the one of the multiple episodes setting. And this is the classical framework for reinforcement learning. The idea here is that we have some environment with which we can interact with. Say, for example, we want to learn a policy that plays chess optimally. We have an environment which is the game environments of chess, and these environments can be reset indefinitely. And here learning happens in between these episodes. So we could have a situation where we kind of spawn our environment, the beginning of the chess game. We interact with the environment in order to complete one episode. And then this gets reset at the beginning, and we use these repetitions of different strategies in order to update our parameters or policies, depending on what we're trying to do. But I hope that it is clear that kind of the point of this slide is that once we choose that we want to learn and approach control through learning, then kind of different algorithms will be better suited for different settings, depending on if we assume we have collected some data sets, some offline data sets beforehand, or on the other hand, whether we want to control some system and adapt to unmodeled effects directly while we are deploying and operating our system, or in the last case, the one of the multiple episodes, where we have an environment with which we have the luxury of being able to interact with. Of course, the boundaries here are not so strict. Methods fall between different categories. So for example, I would say online reinforcement learning typically assumes we have this environment we can reset and iteratively adapt to, but there are methods that still belong to the realm of reinforcement learning, say offline reinforcement learning, which actually fall in the zero episode case. So don't take this too literally, but I think typically you have these three very specific modalities of experience which come into play. Any questions here? Yes?
The key difference between one episode and multiple episodes is that multiple episodes is capable of interacting with the environment and learning through those interactions, right?
So I would say that also in the one episode case, you interact with the environment. In the multiple episodes case, I would say the difference is that you have this episodic nature where you can learn across repeated episodes. So again, I think a good example here is chess. So if I'm trying to learn a policy to play chess, I could play an infinite amount of games and I improve my policy across these games. Here, if we take the same chess analogy, it will be that I'm trying to learn how to play chess during a single game. Yeah.
Sometimes, like, with multiple episodes, that's the only way you can get to other states, right?
Sorry, can you repeat?
Like if you have a policy, if you run it once, you can only get to the states you like go to in that one, versus like getting to different states with multiple episodes.
In the one episode case?
Yeah, I'm asking, like, that's how you get to the other states that you wouldn't get if you go one time through, right?
Yeah, so in the multiple episodes case, if you act differently in the same environment, you would be able to explore different parts of your state space, if this is what you're referring to. Yeah. Yes?
So could multiple episodes be if you deploy a vehicle and then take different time horizons, which do like different actions? Could those be considered different episodes? Or is that still one episode?
So, are you referring to kind of an RL-like approach where I want to...
Like if you're trying to learn like, the the dynamics of the vehicle for instance, like would you cut up like one piloted thing of like some operation into like multiple time histories and then use that as multiple episodes, or is that still one episode?
I see. I would probably classify this in the zero episode case, meaning that you have a data set of trajectories and you're basically chunking this up in order to build a kind of next state prediction or a forward dynamics problem, if that makes sense. Because you're not really being necessarily an agent in collecting that data, right? So here, in the multiple episodes case, typically your policy, your control law, is actually the one that dictates the experience that you have, right? In the zero episode case, you probably don't want a neural net from scratch kind of driving a vehicle, right? Because this will crash for sure. But in what happens in chess is that you have very bad policies at the beginning and then you improve over time. Yeah. Okay. And so given this broader framework, let's approach kind of learning-based control methods, specifically through the lens of classical approaches to learning, starting from system identification. And the problem and the idea of system identification is that for many problems, we don't have to learn online, right? But we could actually have a pipeline where we collect data set of previous experiments or behaviors in a given environment or system that we care to model. And we want to use this data set to build a data-driven model of the dynamics. So in this way, what we can then do is that we can then use this data-driven model to essentially replace our knowledge of the dynamics for control. Right? So the idea is that the overall problem we want to solve, we have a missing dynamical model. We want to learn to approximate this from some data gathered beforehand, and then use this approximate model as a essentially proxy for then using any control tool that we wish to use. And the classical, at least traditionally, method for or tool for system identification is linear regression. And so I'm sure this will be kind of repetition for most of you, but let's just set the notation straight on kind of learning through least square minimization and linear regression in particular. So specifically, we are describing a setting where we assume that we have some system model described as y equals theta transpose z plus some noise epsilon, where y is the output. We have some inputs z. Theta are some parameters which we wish to learn. And then we assume that this process that we wish to approximate is described by some inherent noise epsilon. And the way we want to approximate the system is through examples, which we collect in a dataset D, which are nothing else than tuples of input-output pairs, z, y, with I that goes from 1 to n data points. And we want to use this dataset that we collected offline of examples of input-output realizations to learn to estimate an approximate model of our system. Now, typically, the way we use these examples is through, and the way we learn the parameters theta to approximate our model is through the minimization of some sort of performance criterion or loss, which could be kind of the least squares loss. So something that essentially encodes the difference between the true realizations and our predictions, right? Something of this form. In the slides, we are referring to capital Z as kind of the matrix of the stacked input vectors. Which allows us to rewrite it in compact form as the minimization of the squared Euclidean norm. Okay, and from all our discussions on optimization and numerical optimization, we know that this is a convex function which we wish to minimize. And so we know that in order to, let's go here. To find the minimum of that function, we need to set the gradient of the objective with respect to theta equal to 0. Right, so this is our necessary and sufficient condition for optimality, which essentially means that we want to take the gradient of y transpose y minus 2 theta transpose z transpose y plus theta transpose z transpose z theta, and we want to set this to 0. And by taking the gradient, what we get is negative 2 z transpose y plus 2 z transpose z theta, which needs to be equal to 0, which essentially leads to the solution that we have on the slide, which is basically that the value of the parameters, theta, that minimize our least squares error is z transpose, the inverse of z transpose z, times z transpose y. Okay, so nothing too technically deep or too insightful in this slide, but just to make sure we have the notation in place. Okay, so we're saying that we want to use these tools for system identification. So let us map this framework into the problem that we actually care about, which is using a linear model to approximate our system dynamics. And so specifically, what we're saying is that we are assuming that our system evolves according to the following linear system: xt plus 1 equals axt plus but plus some noise epsilon t. Which we can rewrite essentially more compactly as the dot product between xt ut and vector ab plus the noise term epsilon t. Right, and once we write it this way, I think it's pretty clear to see that this is what we're referring to as our y. These are our inputs z, and these will be our parameters theta, according to the notation from the previous slide. So, in practice, what this means is that we assume we have access to a data set of previous transitions or rollouts of our system. So if you wish, we are assuming we have collected some trajectories that represent possible evolutions of our systems. These trajectories are nothing else than collections of kind of states and controls over time. And we can then use these trajectories that we collected in order to basically construct a data set, which again is tuples of xt ut, which are our inputs, and xt plus 1, which will be our outputs. Right? So this is what we mean when we say we want to learn an approximate model of aerodynamics from data. That is, we will have some mechanism to collect examples of evolutions of the system, and we repurpose these examples essentially as a regression problem, which maps from current state and current control to the next state. Okay, any questions on this? I'm sure this is probably just background for you, but just to make sure we are all on the same page. Okay, so some comments. So in practice, we have shown how the solution to our least squares optimization entails this inverse over Z transpose Z. Depending on how large our data set is, Z could be very large. And so doing this inverse can also be computationally quite expensive. And so there exists a number of recursive formulations or forms for this optimal solution, which essentially enable us to avoid this recursive inverse of a potentially very large matrix that can be extremely expensive in practice. So this is very useful if we have like a stream of data coming in and we don't want to recompute this inverse every time. And of course, here we're dealing with the discrete time formulation, but there exists equivalent also in continuum time. Okay, so here just a couple of theoretical results you might be familiar with. So the first one is that this estimator turns out that it is actually the best linear unbiased estimator for any noise distribution that obeys some common assumptions, specifically that the noise terms, epsilon t, are zero mean, uncorrelated, and all have the same and finite variance. So you might be familiar with this from your statistics classes. And if the noise distribution is Gaussian specifically, then this estimator that we just derived is also known as the maximum likelihood estimator. Okay, so a question that we might want to ask ourselves the moment we decide that this is the mechanism for which we are trying to estimate our known parameters is what are sufficient conditions for which our estimator theta hat converges to the ground truth, to the known and true parameters theta. So in other words, what we're saying is that, say we have an x-axis here which represents kind of the data, the amount of data that we collect, and we have the y-axis here that represents our estimator theta hat. And consider a specific value for the ground truth value of our parameters theta star. What we wish to know is we could see this process of estimating theta hat is itself as a random variable. And what we might want to know is, first of all, if given more data, does this process, is it centered on the ground truth value of theta? And also, how does this estimation vary the more data we collect? And so the reason why I'm saying that we could see this as a realization of random variable is because from the definition, which we just derived of our solution, we see how our estimator theta hat depends on the true outputs y, which is a process that it depends on noise epsilon, right? So we defined before our y's as theta transpose z plus some noise epsilon. And so by just doing the appropriate substitutions, so here we're just replacing the definition of y. And by just doing, reassembling the terms, what we get is that we can rewrite our estimator theta hat as theta plus z transpose z, the inverse of z transpose z, z transpose times the noise epsilon. And so epsilon is indeed some, this is what makes kind of our estimator itself a random variable. And so if this is a random variable, we might want to study the kind of questions we are asking over here on the behavior of our estimator through the lens of looking at the moments of this random variable. So specifically, the mean and covariance of our estimator. Is it clear? what we are trying to do? Okay. So looking at the mean first. First of all, we simply replace our new definition of the estimator of theta hat inside the expectation. Since the only random variable here is the noise term epsilon, we can basically take everything out of the expectation operator. And we see how we can use the assumption that our noise terms are zero mean to basically cancel out this right term. And so what we get is that the expectation of our estimator is indeed the true value of the parameter theta, which is a nice result, right? So what we know here is that in expectation, if we keep using our estimator of the true parameter theta, we will converge to the true value theta. So in this case, we've basically proven that the more data we collect in expectation, the more we will actually be converging to the ground truth value of theta. Okay, so similarly, we can look at the covariance, so how our estimation oscillates around the true value of theta. And we can do, again, some algebraic steps. So first of all, we again just rewrite the definition of theta hat. And then we use this useful identity, that is that the covariance of AX is equal to A covariance of X, A transpose. And here specifically, we define A as Z transpose Z, so the inverse of Z transpose Z is Z transpose, and X as our noise epsilon. And so what we get is this second row over here. And we use, again, kind of one of the assumptions that we were seeing before on how the noise distribution is defined. And specifically, we were assuming, if you recall from the previous slide, that all the noise terms epsilon t are uncorrelated and all have the same finite variance. So this essentially means that our covariance matrix for the epsilon values is something that only has zero terms everywhere, except from the diagonal where we have the same variance. Where here we're assuming the variance is sigma squared. Right? Which essentially means that we can do this substitution over there. So again, doing some algebraic steps, I think the bottom line is that we get an expression of our covariance, which is the variance sigma squared, multiplied by the inverse of our summation terms that goes from 1 to n of basically different combinations of our states and controls. Now, from the perspective of our estimation process, we would like the covariance to basically go to zero the more data we collect. Right? So we want our estimation to be more and more centered around our expectation. And so this means that in practice, since this is an inverse and so this it goes at the denominator, what we want is that this summation from 1 to n, the more n grows, this has to go to infinity, so that the overall thing goes to zero. And so what we're saying is that, first of all, this is a neat result again, in the sense that as long as if our system operates forever and it operates in a non-trivial way, meaning that the x's and u's that we observe are non-trivial, for example, just statically stop to zero, then that summation will go to infinity, and so our covariance will go to zero. So here I meant, when I refer to as non-trivially operating the system, what I meant is that I refer to this characteristic that is known as persistent excitation, which essentially encodes this idea that we have to continuously probe the system in meaningful ways. And if we do so, then to the limit of n that goes to infinity, also our estimator will be exactly around the true value of theta. Okay, any questions here? Yes. Oh, sorry.
was wondering, is there an intuition on why this is invertible enough as to work?
Sorry?
Like, is there an intuition why this is invertible enough as to be meaningful? Like, I mean, what is a supportive condition or something like that?
Mm-hmm. No, sure. So there is, here we're kind of simplifying the treatment. There is some, I can definitely refer you to the complete derivations that basically will tell us when this is invertible. But this is just as a frame of reference, kind of considering that our goal here is system dynamics and estimating these true parameters theta. I was just kind of fast tracking to the overall result, saying that if we use linear models to estimate our dynamical systems, and we use this estimator for theta, then we get something that is unbiased, and that under some regularity conditions, basically also converges with zero covariance, if that makes sense. So there are some regularity conditions that I'm happy to refer you to. No. Yeah. Okay. And so in practice, kind of system identification kind of leads to a number of questions, right? So we're describing this overall framework or paradigm where we want to essentially approximate the system dynamics by learning from data. And so some questions that could emerge is, what if we have a data budget? So how much data is required to learn the model? Or how can we even quantify what good means in terms of parameter estimation? And interestingly, so we did all of these analyses from the perspective of a statistician wanting to analyze the performance or the behavior of an estimator of our parameters. But in reality, what we care about is control performance, right? So we do not really care too much about model accuracy. What we care about is that we get a better controller out of this process. And so, again, just to make a visual discussion here. So consider the case where we have a very extreme case where we have depending on some parameter theta, which we don't really know the exact value of, depending on the parameter theta, our control law would vary wildly. So say that if theta is negative, we would have one specific control that we have to take. And if theta is positive, we would have a different control that we have to take. So a very kind of stepwise control function depending on theta. And say that the ground truth value of theta is over here. Now, consider these two different estimates for specifically theta 1 and theta hat 2 for that same parameter theta. Of course, kind of the one on the left is, from a purely statistical point of view, or at least distance-based here, is worse, right? Because it's further off. But from the perspective of control, since we are on the right side of the sign, this would actually lead to the controller having better performance, right? So of course, this is a extreme case and completely pictorial, but this is exactly the intuition that I'm referring to. And in a way, this is one of the main kind of downsides or bottlenecks of these system identification approaches, because we are introducing this intermediate objective that is model estimation, which is not necessarily aligned with controller performance. Okay, some other question is, so we are assuming we have access to a data set. How do we collect this data set? What if we are learning while we collect the data set? Or what if we have some safety considerations that have to be done while we collect the data set? Of course, we need to take this into account because we would be operating in a system with only partial knowledge of what the system is, and so we might want to be more conservative. And lastly, here we are assuming we are doing everything under this linear assumption. So we have a ground truth linear model, and we are trying to estimate the parameters of a linear model. So the family of models actually matches. But in reality, we don't really know how the system behaves sometimes, right? And so there's an entire discussion on, is our family of models that we're trying to estimate expressive enough to include the dynamics that we actually wish to learn? And so there is a trade-off between how much data we have, what is the expressivity of the model we want to learn, and so forth. Okay, any questions on system identification before we move on to adaptive control? I mean, I guess the main idea here is pretty simple, right? So we want to estimate a model from data and then use this potentially to improve our controller later on. Okay, but so let's move to adaptive control. And if system identification was essentially lying into this 0 episodes setting, where we had this data and we wanted to use this data to estimate a model of our dynamics, adaptive control falls into this 1 episode setting, whereby we want to improve our control essentially through online adaptation in real time as we operate the system. And so this can be done, again, as we were saying before, by either directly improving the controller or by first learning a model and then using this model to improve the controller. And this is what differentiates between model reference, adaptive control, which essentially falls in the first category, where, as we will see, we're directly improving the controller, or model identification, adaptive control. So notice identification also in the name, which falls under the second category, where we are first estimating a model and then using this to improve the controller performance. And I would say that kind of literature in adaptive control, it's pretty traditional. So it dates back to a number of years ago. And I would say that in general, the classical setting is that it does not consider the optimal adaptive control setting, whereby by optimal I mean we are not necessarily optimizing for some performance metric or cost, but I would say that adaptive control strategies are typically focusing on proving the stability of the coupled system, which entails the coupling of the controller, the adaptive component, and the system dynamics. So how we will see is that we won't be necessarily optimizing for some performance metric, so minimization of some cost function, but we will be studying the stability of the coupled closed-loop dynamics that emerge from the definition of a specific controller, which we have to come up with, of an adaptive component, that is how we adapt the controller based on experience, which we have to decide, and the system dynamics. Okay, and so as a brief recap and detour, kind of the tool we are using throughout this class to analyze stability is the one of Lyapunov stability. And specifically, as we discussed last week, we defined the Lyapunov theorem as follows. So we're given an autonomous system, x dot f of x. Note that we can easily represent kind of systems that are controlled through some policy x as an autonomous system, whereby we are directly encoding the effect of our control as a function of the state, pi of x. So we're given an autonomous system, and we have an equilibrium point, x star, such that the dynamics f at x star are equal to 0. So this is an equilibrium point for our system. So last time we introduced Lyapunov stability as this, we saw it from a very pragmatic lens as this tool that enables us to derive stability properties of the system. And we did this from the perspective of, according to the Lyapunov theorem for global stability, if there exists a function that satisfies some characteristics, which we'll see briefly, then this equilibrium is globally asymptotically stable. I think last week we only discussed the local versions of this, so we're not really looking at the global stability, but we are reinforcing this today. And specifically, the conditions is that we need to find this Lyapunov function, v, which respects these 3 conditions. The first one is that v of x, so it has to be, the function v has to be positive for all x that are not the equilibrium point and 0 at the equilibrium point. The derivative, v dot of x, has to be negative for all points that are not the equilibrium. And the third property and the third condition that we have to respect, which is the one we are using to strengthen our conditions for global stability, and this is also known as radial unboundedness, is that as the norm of x grows to infinity, also the value of the function grows to infinity. So visually what we're saying is that we have a system of an x1, x2. The Lyapunov function is something that is like ball-shaped, and that following the dynamics of the system, it essentially dissipates energy and reaches the equilibrium point, right? So this is positive everywhere except at the equilibrium where it's 0. And the third condition essentially says that this keeps growing the more we go further out. And we discussed as this was essentially an extremely useful way of approaching the stability property, because we don't have to integrate our dynamics or solve these for every possible conditions, but we just have to define a function that respects these properties, and we can draw conclusions about the stability of the system overall. Okay. Any questions here? This is mostly repetition, but any questions on so far? Okay. So what we'll be doing going forward is that we'll be using this Lyapunov stability theorem to prove stability of kind of coupled system dynamics, controller, and adaptive component mechanisms. And so here we take a little step back. We open this parenthesis where we show exactly what we mean by doing these Lyapunov stability analysis on a system that doesn't really entail control at all, but just to show you how we do these stability analyses, which we will then be doing for the purpose of adaptive control. Okay. So let me make some room here. Okay, and so let's consider the system composed of a mass spring damper system where we have some mass m on which we apply some force F. We have a spring K, and we have a damper D. We want to prove the stability of this system to the 0 point, specifically 0 position and 0 velocity. And to do this, we will assume and we will consider that the energy of the system is our candidate Lyapunov function. So the system is described by an energy function E of x dot, which is 1/2 k x dot plus 1/2 m x dot squared. So essentially a combination of potential and kinetic energy. And so what we want to do is, given a candidate Lyapunov function for our system, we want to check those 3 properties that we were describing in the previous slide. So in this case, condition 1 and condition 3 are easily derivable by inspection. So we can see how this energy function is positive for all x and x dot, unless these are equal to 0, so our equilibrium point. And we can see that as x grows, also our energy function grows. And so we'll focus on our analysis on proving the second of the 3 conditions. That is that the derivative of our function, in this case the energy function, is negative for all points that are not the equilibrium. So let us do this. So let's compute the derivative of the energy function, E of x dot, which is equal to k x dot plus m x dot x double dot here we can use the fact that from our system dynamics that we know that m x dot is equal to negative dx dot plus kx. to essentially rewrite this as k x dot minus x dot times dx dot plus kx. From which we know that these two cancel out. And so we get essentially the result that we have on the slide, that is negative dx dot squared, which indeed verifies our second property, because this is indeed always negative besides from the equilibrium point. Okay, so this is indeed what we mean by performing a stability analysis through Lyapunov theorems. Okay, so let us now move to what we actually care about, which is adaptive control techniques. And so specifically, let us start from model reference adaptive control. So in model reference adaptive control, we essentially will be defining 4 key elements or parts. So the first one will be a plant containing unknown parameters. So the plant here is a very specific word, but just let's consider the system. So this is the system where we have some unknown parameters. We will be defining a reference model, which essentially compactly specified the desired output that we would want to have from our system. In a way, the reference model can be seen as an alternative way to specify performance. Right? So we are not really measuring performance through the lens of a metric or objective function that we wish to optimize, but we measure performance from the perspective of measuring distance with respect to a reference signal. The third element is that we will have a feedback control law that contains some adjustable parameters. So we will be coming up with a control mechanism or control policy, which depends on some parameters which are adjustable. And in particular, we will be adjusting these parameters according to an adaptation mechanisms, which we will be, tasked with coming up with. Any question on the setting? Okay, great. Okay, so now we will be going through an example of the kind of analysis that we might be doing on in adaptive control. We will be, first of all, setting up the stage in a setting where everything is known. So we'll be just doing the analysis when we actually don't have unknown parameters and adaptation mechanisms. And then we will be taking that same example, but now adding this adjusting component and repeating the analysis. Okay, but as a frame of reference, remember that in adaptive control, we care about measuring the stability of the coupled system controller adaptation mechanism system, right? So this coupled system. And so in general, we will be defining our 4 ingredients. So we'll have a system which might have some unknown parameters. In this case, we consider a double integrator system. So for us, the system will be mx double dot equals u. We said before that we want to measure performance as distance with respect to our reference output that we wish to have from our system. And specifically, for us, the reference will be described as through a fictitious variable, which we introduce, x sub m, which represents the essentially the version of our state x, which we create this kind of fictitious model in order to represent it. So we assume we have someone giving us positioning command RT, and we come up with this ideal response of the controlled mass, which we assume evolves according to this differential equation. So we're introducing this fictitious xm, x sub m, and we hypothesize that our system will evolve according to this reference model. So x sub m stands for model. So specifically, our reference will be x double dot, xm double dot plus kd xm dot plus kp xm equals kr of t. Right, so x sub m will be our ideal output. The various k's here are just gains we can choose as a system designer. And we assume that r is a positioning command that is given to us. Okay. So now we assume that the mass is known exactly. And we can basically state the fact that if the mass is known exactly, we know that we can achieve perfect tracking of our reference model through that control law. So the control law specifically is that u is equal to m times xm double dot minus 2 lambda x tilde dot minus lambda squared x tilde, where we are denoting as x tilde as the difference between the output of the actual system and the reference, the ideal output that we would want from the system. So if we want the tracking error. Right, so you see here as we are building the different ingredients of our adaptive control pipeline. And you might wonder, like, where is any of this coming from, right? The point is that if we were actually having to design this system, we would be tasked with designing these things ourselves. So we would be having to, we would have to come up with a reference signal which we think is appropriate for our system. We would have to come up with a control law which controls our system, which again we think is appropriate. But the purpose of this is that we are assuming that someone gives all of these elements to us, and we are showing the kind of stability analysis that follows once we have these ingredients. In reality, there is obviously an iterative component where maybe we have a system, we try out a specific type of reference model, we see how it works, and then maybe we're not really able to prove stability, and we keep iterating on this. But for the purpose of this stability analysis, this is the kind of setting we're in, right? So we have a system, we define the reference, a reference that we wish to track, and we have a control law which exponentially converges to the zero tracking error. So to show that this is a control law that basically converges to zero tracking error, we have to derive the closed loop dynamics of this combined system. Is it clear what we are trying to do? Okay. So let us start from our system dynamics. So mx double dot equals u. So we have just defined u according to this control law. And so we can basically replace this as x double dot m minus 2 lambda x tilde dot minus lambda squared x tilde. Which we can rewrite as m times x double dot minus xm double dot plus 2 lambda x tilde dot plus lambda squared x tilde, just to be equal to 0. So we just brought this term on the other side. Now, from our definitions, we know that this is x tilde double dot. And so we see that we can essentially discard m because this has to be equal to 0. And so if we solve this ODE, the solution of the ODE is actually that x tilde t is equal to C0 plus C1t times e to the negative lambda t. Right? Now, we know that lambda is a gain which we choose, and this gain is positive, right? So we know that lambda here is positive. So what we can say is that as t goes to infinity, then this, so x tilde t goes to 0. Right? But what does this tell us about tracking error? Yes. Yes, exactly. So we defined x tilde as the tracking error itself, right? So we defined it as x minus xm, and we know that this goes to 0. Okay, so this was basically, we introduced the overall setting. We hypothesized the mass m was known, and we basically said that this control law was, the control law that guaranteed convergence to 0 tracking error, and we have motivated it by this analysis over here. Now we go into the setting that we actually care about, which is the one where we assume that the mass is not known exactly, right? So here we assume that everything basically stays the same, but now we are in the slightly more realistic setting where the mass is not known. And so we will have an estimate for the mass m hat. Okay. So now let us once again derive the closed loop dynamics of this combined system. Okay, and to do this, let us do some definitions just for notational compactness. So we'll define S as x tilde dot plus lambda x tilde. We'll define nu as xm double dot minus 2 lambda x tilde dot minus lambda squared x tilde. And we will define m tilde as the estimation error, basically, m hat minus m. So given these definitions, let us essentially do the exact same analysis we did over here. Right? So we will derive the closed loop dynamics of this combined system. So we start once again from our dynamics, mx dot equals u. We know what u is because this is something we defined. But this time u is a function of the unknown mass m hat, right? So m hat times xm double dot minus 2 lambda x tilde dot minus lambda squared x tilde. This is nu. Right? And so we get m tilde nu plus m nu. Right, where basically here we're using the fact that m hat is equal to m tilde plus m. from the way we defined m tilde. And so this leads to our closed loop dynamics defined as m x times x double dot minus nu m tilde nu. Which we can expand as m times x double dot minus xm double dot plus 2 lambda x tilde dot plus lambda squared x tilde equals m tilde nu. Where this is x tilde double dot. And so we basically get what we have on the slide. So we have m times s dot plus lambda s equals m tilde nu. Right? So nothing too deep here, just some algebraic manipulations. But here we are again defining this coupled system, and we are computing the closed loop dynamics of this coupled system. Okay, so now what we want to do is considering a specific way of adjusting our estimate, m hat. So remember that we are interested in doing these adaptations, and so we need an adaptive component in the picture. And specifically, we assume that we will be adjusting our estimate, m hat, as according to this law, that is m hat dot is equal to negative gamma nu s, where gamma is again a gain which we call an adaptation gain and has to be positive. Right? Okay, so basically now we have all of the ingredients to perform our stability analysis through Lyapunov. So what we're going to do is we will be considering this candidate Lyapunov function, and we will use this to basically verify that the system is globally asymptotically stable to an equilibrium point. And we'll study what this equilibrium point means, essentially. Okay, so we have this candidate Lyapunov function defined as 1/2 times ms squared plus 1 over gamma m tilde squared. Remember that according to our Lyapunov analysis, we have to check for our 3 properties. Which are, again, these ones here on the slide. So once again, the first one and the third one are easy to prove, and I'll leave this up to you guys. And so we'll focus on the second one. That is that the derivative of this Lyapunov function v dot has to be negative for all points that are not the equilibrium. And so we'll be computing the derivative v dot, which is equal to ms s dot plus 1 over gamma m tilde dot. So here we use the fact that m tilde, as we defined it, is equal to m hat minus m. But because m is a fixed mass, so it's a constant, from this we can say that m tilde dot is equal m hat dot. Right? Yeah. Okay. And so what we get is ms times s dot plus 1 over gamma m tilde times m hat dot, which is equal to ms s dot minus 1 over gamma times m tilde gamma nu s. Right? Where here we just used basically the fact that m hat dot is equal to negative gamma nu s, according to how we defined the adaptation component. Which essentially leads to the fact that the derivative of our Lyapunov function b dot is equal to s times ms dot minus m tilde nu. Where this is minus m lambda s, and so we basically get the result on the slide, right? So we know that, well, we can write here. Yes, so minus lambda m s squared, right? Which basically confirms validates the second property, specifically as a function of s in this case. And so what this is saying is that since we have been done this Lyapunov stability for given this candidate Lyapunov function, what we can say is that we can say that S goes to 0, because we are considering this as our candidate equilibrium point. So S goes to 0, and so remember how we defined S, which is x tilde dot plus lambda x tilde. What we're basically saying is that we have shown that this quantity goes to 0, which means that x tilde dot is equal to negative x tilde, lambda x tilde. Where lambda is positive, right? So remember that lambda is positive. And so we've shown that S goes to 0, and so this means that x tilde dot converges to, tends to this. And so visually what we're saying is that our system, if we were to express it in a plot as a function of x tilde and x tilde dot, is something that converges to the line x tilde dot equals negative lambda x tilde, right? So it's something that as t goes to infinity converges to this line. And specifically, once it's on the line, if x tilde is negative, the derivative of x tilde will be positive. And so it will tend to grow. On the other hand, if x tilde is positive, the derivative will be negative, so it will tend to decrease. And so we have shown that the system will essentially be converging to this line, and once on this line, it will be going to 0. Why do we care about this? It's because if x tilde goes to 0, we know that x tilde is our tracking error, essentially, and so x minus xm also goes to 0. Right? Yes?
Sorry, how do you stop in the bar or here proof of this approaches?
So here we were using the tool of Lyapunov stability to essentially prove, stability of the system to an equilibrium point. Specifically, this candidate Lyapunov function is defined as such, which is basically a function of S in this case here. And so we have verified explicitly the second of the three properties, but the other three are more easily shown by even just by inspection. And we know that if candidate Lyapunov function satisfies these three properties, it shows that the system will be globally and asymptotically stable to the equilibrium point, which in this case for us was showing that the system will essentially be globally asymptotically converging to S going to 0. And we showed then this analysis whereby if S is going to 0, then the tracking error will also be going to 0. So this is in a way like a one-to-one mapping and application of the Lyapunov stability theorem. Does that make sense? Yes?
In this case with unknown mass and the previous case with known masses prove convergence, like stability, but not actually computing gamma or computing lambda.
No, so indeed, let me take a step back. So specifically, the general setting we're working with is we are introducing adaptive control. And we mentioned that classically, adaptive control is instantiated as having to come up with a coupled system of different ingredients, namely a system, the controller, and an adaptation mechanism of some adjustable parameters. And the entire problem will be posited as we want to derive and prove the stability of this coupled system, right? So specifically what we have shown before is that we basically constructed towards this example by first introducing the case where M was known, and we just proved the stability of that overall system. Now we are introducing an adaptation mechanism in order to adjust our estimate of M. And these adaptation mechanisms rely on some gains that we are introducing. In practice, we would have to tune this gain, if that kind of now to answer your questions more directly. So I'm aware that I would say this analysis can feel, somewhat intricate and complex in the sense that we are introducing a lot of functions, which is kind of unclear where it comes from. We're introducing control law, which is also unclear where it comes from, and same thing for the reference. The reality is that if we were to, study this explicitly, this would be an extremely case-specific discussion. And so I think for the purpose of this class, not very meaningful. So the reality is that whenever we have a system and we wish to apply adaptive control for the system, we will have to be doing some studies and analysis on ways of deriving all of these components, deriving the reference, deriving the control law, deciding how I want to adapt my adjustable parameters, and also deriving a candidate Lyapunov function. So a lot to take in. But then kind of what we decided to focus on for the purpose of this class is showing that once we have all of these ingredients, what are the stability analyses that come as a result? Yes?
This analysis with unknown mass hinged on that particular Lyapunov function, right?
Yes.
How did you get that?
Yeah, this is the point where we are completely kind of fast tracking. The reality is that if you have an interesting system and you derive a Lyapunov function and you show that the system is stable, you write a paper about it and you're happy about it. So this is something where it's extremely case dependent. We won't go into it. I think there are a number of references that actually I think the next slides is exactly on this. So I definitely advise you to look into this reference over here to basically see if you wish, the forward direction of this discussion. So until now, we've basically been assuming that either us, a previous version of us, or someone incredibly smart is giving us all of these things, and we just analyze it. But in practice, we have to come up with it. All right, so I'm out of time. So I'll conclude the discussion of MAIAC next time, and see you on Wednesday.